Hello everybody and welcome to Unit 6. We're going to cover igneous rocks and these nice flashy things here, volcanoes. So first we have our diagram here with our different cycles. Mostly we've been focused on this part of it here with tectonics, but we are gradually moving a little more into this part with the rock cycle. Everything from here, the magma, igneous rock, everything that's going on in this section, melting by subduction included, as well as everything that happens here, rock of the mantle leading to magma, just to get an idea. So these are the things in question. This is what we're talking about. These are all, I believe, igneous rocks. Everything from these, what you would call just regular old granites, it looks like. You have large crystals with no discernible real pattern with them, just interlocking big crystals making up the rock. Have something like this, which is still pretty clearly made of crystals. Again, no discernible sort of patterns or fabric to it. Seems mostly like a pretty random arrangement of these little mineral grains, smaller than this one, I should say. You have these two, where the grains they're there, but they're so small that you can't really make out individual grains with the eye. You can maybe see, little bitty pieces and things, but you certainly can't see all of the individual crystals in these. You can also spot here little spots where gas bubbles would have escaped from the liquid as it was cooling. And something like this, where you have these larger crystals embedded in a ground mass, this sort of gray wasteland of ground material next to it. So you have these big grains, and you have what we call a matrix of smaller grains, the little gray material in between. Section 1 is going to cover molten rock. What do we mean? So this is what we're talking about when we say molten rock. Rock which is hot enough to have melted. If it is below the surface of the earth, we call this magma. If it is above, we call this lava. And it begs the question, actually, we go back to this last diagram here. So what's down beneath where my cursor is? What's below the diagram? Or does the magma form right here and then come up? Does it come from somewhere much deeper? Where does the magma come from? So just to review, we have our thin outer skin, rigid crust of the earth. We have our partially liquid thing here, mostly solid, 99% solid, a little bit of molten rock mantle. We have our liquid outer core and a solid inner core. And you would think maybe that this magma comes from the outer core here, the liquid portion. That is by and large not correct. Most of it is going to come actually from the very uppermost mantle to the lowermost crust. That's why I have the arrow right here in between them. If we put it in heat terms, this is a bit of what we're looking at. So the magma zones are all the way up here. If we have the center of the Earth, we have the surface of the Earth, most of the magmas are going to come up here, the very uppermost portion of the mantle to the lowermost portion of the crust. You can actually see we have these beneath little subduction zones, here beneath little spreading centers, divergence zones. So where does magma come from? This is something which comes from the partial melting of uppermost mantle and crust material. As mantle material moves upward or has water added to it, it begins to melt. And once it melts, the density of the material gets lower. And since the density is lower, it is not pulled down by gravity the same way that the really dense stuff around it is. And so it begins to rise up. This is exactly the same as a hot air balloon rising. Well, hot air rises. This is the same. As the air heats up, it becomes less dense, so gravity doesn't pull on it quite so hard. And this is why when we have our liquid, we can be most assured that sooner or later it is going to make its way towards the surface if there is any possible path to do so. As it rises, gas molecules which are dissolved into the magma come out of it, and the magma begins to build in terms of pressure until it reaches such intense pressure that it overcomes the strength of the rock between it and the surface, and it bursts out, and we have an eruption. So there are a couple different methods which we can use to melt earth material, right? The most common we're going to be talking about is through a reduction in pressure. So you have some sort of area, you might imagine a mid-ocean ridge, some sort of divergent margin, a place where plates are pulling apart, and as they do so, they create this zone of low pressure, right? You have things rising up in the middle where they're pulling apart, and as it rises, it starts to get less and less pressure, which you could think of as less force, which is holding it together, holding it to be solid. So if we have all this pressure on the material, when it's deep in the earth and it starts to rise up, and then we take that pressure away, it's going to expand, it's going to melt, because there's no longer all this force which is holding the molecules to be very, very tightly together. Just for an example of this, if you boil water at high elevation, this is easier because there's less pressure which is holding molecules in the water together. So if we go up to a high elevation, there is less atmosphere pressing down, less pressure, and so it is easier to boil water. We can also have wet melting, call it flux melting here. So at the subduction zone, it is not just the plate itself which gets dragged down into the mantle. The plate drags with it all of this other stuff, including water and carbon dioxide. And as it drags the rock and the water and the carbon dioxide down and gets deep enough, the liquid water is removed from everything in the body of the rock, and it starts to actually lower the melting temperature of the rock. So it's much easier to melt this sort of thing under wet conditions than it is dry conditions. So the plate subducts down, it gets low enough, it starts to dehydrate and shed off liquid water, which it had carried with it in crystal form. And then that liquid water lowers the melting point of the materials in the rock and causes it to melt, rise back up to the surface. This is why we see volcanoes and volcanic activity associated with subduction and associated with convergent margins. It is because of this process. You can see a little bit of the overview on this. So this is just graphically trying to show the origin of deeper magmas. We'll get to the words here, basalt, andesite, and rhyolite in a bit. We have a bit of a visual for what is going on at subduction zones and convergent margins here, how that leads to volcanism, as well as cases where we might have isolated, and we'll get to this in a bit, these volcanic ocean islands. We're going to talk about three kinds of magma for the most part. We have basaltic, andesitic, and rhyolitic. The terms aren't important for now. What you should know is that we have dark magmas, which flow really, really easily. They're thinner almost. Right? We talk about them being low viscosity. If you pour this magma onto the table, it spreads out immediately in all directions. It flows very, very easily. These are dark magmas, which come from very, very deep in the earth. And I say dark, I mean low silica content. We'll get to why I'm putting it that way in a bit, but just remember, these are the ones in the middle. Think about these as being gray magmas almost. These are a little bit more sticky than the basaltic magmas and tending to explode somewhat violently. And then you have the rhyolitic magmas, stuff which is lots of silica, our white magmas coming from the crust, very, very viscous, sticky stuff. You think of like pouring honey out, how it moves very, very slowly. You pour honey onto a flat surface like a table, and unlike something else which would spread out right away and flow across the surface of the table, instead it moves very, very slowly. It's this sticky, gobby stuff. And these tend to lead to very, very violent eruptions. The pressure tends to build to huge amounts before it actually gets set into motion. So what is the difference between these? So we would talk about composition. So the stuff which comes from really, really deep in the earth, stuff which is coming from the mantle, is going to be low in terms of the amount of silicates. Consider these darker because what it has instead of silicates are things like iron and magnesium, these metals, things that give it dark colors. And you have all the way up to 75% even for the stuff which comes from the crust, the lighter colored, the whiter magmas which come from shallower depths, which might be all silicates. And when I say silicates, I don't know if I have it here. We're talking about SiO2, right? We're talking about silicon and oxygen. Those are the two. These also have water vapor and carbon dioxide in them. It's never just liquid rock. There's almost always these other things, gases and water that they carry with them. We call these volatiles for good reason. In terms of temperature, so the stuff which is coming from deep in the earth is going to be hotter. The stuff which comes from shallow in the earth is going to be a little less hot. And things which have a lot of water content are going to melt at lower temperatures, just like when you have the slab subducting at a subduction zone, a convergent margin. Because there is a lot of water, it melts very easily. Finally, we talk about the viscosity of these and how well they flow. So stuff which comes from really, really deep within the earth is going to flow really, really easily. It spreads out. It's sort of thin, depending on silica content and temperature, right? So the stuff which is high temperature and low silica content flows really, really easily. You can imagine that the silicates are these nice chains holding onto each other, binding everything together. And when you have a lot of those, it is really hard to spread things out. When you have only a few of these chains holding the magma together, it's very, very easily to spread it out. So stuff which is low silicate is going to flow easily because it has low viscosity, low flow resistance. What we mean by viscosity here. So something which is less viscous is going to flow very easily. Something which is really viscous it's like a thick liquid, very, very hard to get these to move. It is dependent, on silica content here. So with a lot of silica, it is hard to move in any way. It resists everything that you try to do to it. The silicons bond really, really strongly to each other. And this puts everything that we've talked about so far into a table. So we have our rhyolitic magmas. Think of our light-colored stuff, white magmas coming from the upper part of the crust. It is not actually white in color, I should specify, but it's easier to think about it this way, I promise. Stuff which is mostly silicate, low in terms of iron, magnesium, and calcium, so low in terms of these certain larger metals, and high in terms of alkali metals, potassium and sodium here, low temperature, high viscosity, high gas content. So because this stuff is so viscous, it's so sticky, it tends to bring a lot of gas with it. We have our stuff that is in the middle here, and finally our darker stuff, basaltic lavas. So low silicate, lots of iron and these other metals, low in terms of potassium and sodium, hot, spreads out very easily, and because it's so thin, it doesn't tend to trap a lot of gas in it. So looking at this one more time, you might expect, right, we have our upper part of it where andesite and the rhyolitic magmas come from, deeper parts which carry the basalts. And andesite, we're talking about all the stuff in the middle here. Finally, I don't expect you guys to memorize this. I know you see this and you're thinking, he can't make me read that. I won't read that. You don't have to read the entire thing. This is way too much information. But for now, this is how we're going to talk about things. We have texture, which is a matter of where the body, the molten rock, either lava or magma, is cooling. It's fine-grained, usually, if it cools near the surface. This cools very quickly and makes small crystals. There's not a lot of time for the crystals to grow. Or they can be coarse-grained. Have really big crystals. These form deep within the earth because there is a lot of time for the slow crystals to grow and grow and grow. And over here we have composition. So felsic, we're talking about the whiter stuff, light-colored, rhyolites. Over here, mafic, the darker stuff, basaltic. Section 2 will cover igneous rocks. Thanks.